Hey guys, welcome back to my new videos on closed loop control of three-phase front-end converter using Matlab Simulink. A circuit diagram for the three-phase front-end converter is shown here. Here we are sensing the uh, VABC voltages as well as the current for each phases, and we are converting that into the DC. And here the three-phase ABC voltage is converted to the rotating DQ frame. So and we are calculating the theta, and the theta will be given to the ABC to DQ frame. And similarly for the current also we are converting from the ABC to the DQ frame. The voltage and current controllers is here. We are having the VDC reference will be setting. The voltage controller will be there. The saturation limit will be there, and we have the current controller and saturation will be there. The feed forward term will be there, and this cancellation terms will be there, and the saturation limit will be there. And this is the feedback, uh, and the VDC will be which we sense. We are feedbacking that voltage is here, and after getting the here we will get the VD reference and VQ reference, and we need to convert that into the ABC. And we have to, after getting the ABC, we have to convert given to the pulse width modulation to generate the pulse width sinusoidal pulse width modulation and feedback to our circuit, the MOSFETs. The design specifications are: the input voltage will be the 400 BMS RMS voltages and 50 Hz. The output voltage will be the 800 volt DC. Switching frequency is 10 kilohertz, and the rated power for this converter is 10 kilowatts. The capacitance of the DC link capacitance will be 0.5 millifarad. The allowable voltage range means the 20 percentage of the phase voltages. The internal resistance of the inductance is 10 ohms, and the T1 and T2 of the converter is 10 microsecond. Now let's open our Matlab Simulink. Let us search for the required libraries. Items are voltage source, current measurement, voltage measurement, MOSFET, RLC branch, change to 325 and 50 Hz. Change the phase to the minus 120 degree. For this, minus 240 degree. Change to RL, and R will be 10 milliohm, and inductor value will be 10.2 milliohm. Okay. Now connect the MOSFET across it. Okay. A phase to the leg A, first leg, and P phase to the second leg, and C to the third phase. Okay. Connect drain to drains. And source to source, and required a capacitor. Just consider 64, change to C value, and it will be 0.5 millifarad. Okay. And we need to measure the voltage as the load. Let's go to block and name these two ADC. Okay. Now measure the per phase voltages for each. Okay. Let's go to block. Change to IC, IB, IA. Okay. Name to VA. This to VB. And the third is BC voltages. Okay. Now for designing the PLL, we had already designed the PLL for this. You can check the description for design of PLL using Matlab Simulink in the playlist. Okay. I'll just copy this, the AVC2, and I will make a conversion for the current as well. Okay. And these two I. Okay. AB, IC. Okay. And this will be here also. Need to change this. and we need to include the transfer function and the gain as well here. I'm just changing these to I A I B and we see. Okay, this will be I alpha. Okay, this will be I beta. Now here also we need to change from B to I. I will be required. This will be I. This will be ID. This will be IQ. Okay. PLL we are already designed, so no need PLL. Here need to include the transfer function. Okay. And transfer function will be current transfer function will be the 1 by 10 e power minus 6. Okay. And we need to one thing, we need to modify the gain value as well here. That will be 1 by 3 into 20.49. Okay. Okay. Similarly for the third phase as well. Current IC. Okay. And now here we have converted this from change to IT and this to IQ. Okay, and this required at outer side, so we will connect one out block, out pin, and name these two IQ and remove this one. So our ABC2 DQ has been done. Next is we have to connect this I here, IB here, and IC here. And this theta will be going to be changed to IQ. Okay, and these two ID. Yes. Okay. Now we have what we did means till now we have converted ABC to alpha beta and alpha beta to DQ, and we also designed for the PLL. You can check out our playlist. In the description I will add the PLL videos. So we have already done this person there, and we also need to transfer the IABC to DQ IDQ. Okay, and after that we need to design the voltage and current controller. So I will required is PD is required. After that DC is required, ID, IQ, okay, and the theta value is also, theta is not required now, and we will just subsystem, create a subsystem for this. Name this as BDC. Okay. For this ID, and this as IQ. Okay. This as PD. Now we are going to design our controller, voltage and current controller. So we required constant block, constant sum, same to plus minus, and BDC will be required with our transfer function as well. Transfer function is there, and feed forward, and this transfer function will be 1.25 5 bar minus 3, and voltage will, and the denominator will be 10 e power minus 6. Okay, we have done with the voltages feedback, and we require another subsystem. Okay, this subsystem here will create a PI controller here or here. So required gain, okay, gain and sum as well, sum block. Just copy this as, and required one integrator limited. Okay. Change this way, upper value is 1 and lower value as -1, and change this value to 10. Okay, and these two the 1000. Okay, so voltage controller has been designed. Now name this as voltage controller. Voltage controller. Now take the saturation and limit the saturation from 1 to -1. Okay, required another sum block, change to plus minus, okay, and connect to we need ID, required just copy this voltage controller, voltage PID controller, just copy the sum block as well, connect to one saturation block here, one more time the sum block, okay. Just change this value to the negative. Also this will be plus plus, and this will be minus minus, and required one more saturation block here over. Okay, now required a gain block, and the gain will be 1 by g, that is into VDC. So 1 by g will be 1 by 400, that is 1 by 400 going to given. Similarly, another for this we require ISD into omega into LS. For that we need to create two gain block. Okay, and this value will going to be 2 pi into omega, means omega into omega ls into I q. Okay, that will be 1000 e power minus 3, 1000 e power minus 3 into pi. Okay, I need to connect to the q. Now just copy this. We require this only person, and just required a constant. Okay, set value as 0, the current value will be 0, and this will be going to be 1 by IQ current, and saturation will be there, and some block this will be minus and plus, minus and plus, and this will be going to be ID. Okay, just connect the, copy this one block here, and this will be omega ls into ID, that will be there, and it will finally give our. Now name these two VD star, VD star. Okay, and name these two PQ star. So we have these are the control output which we will get. Okay, now we need to convert it from DQ to alpha beta and alpha beta to ABC. So just require a subsystem, another subsystem. Connect VD, PQ star. Here we need to convert from ABC to alpha beta, DQ to alpha beta. So required are, let's consider gain block, one gain block. Okay, and search for sine block, change to this cos function. Okay, and we need another theta value here as well. Just in in and name this as theta. Theta value and required divide by search for divide by, change to multiply. Okay. Now for this, the V alpha will be the BD cos theta minus BD sin theta, BD cos theta into BD sin theta. That will be quite a symbol of 1. Change these two plus and minus. Okay. And for another for here, that will be D into cos BD BQ into sin theta, and plus to the plus and minus to this, and this will generate the alpha. Okay. Now the another is B D sin theta plus BD sin theta plus BQ cos theta, BQ and cos theta. Now add these two, change to plus plus, and name these two as yeah. So we had generated the from ABC to alpha beta, DQ to alpha beta, and now we need to, here the theta is required, so we will connect the theta as we had already calculated the theta value. And next, after that, we need another subsystems which will convert from ABC alpha beta to ABC. Okay, so here let's connect alpha beta, and for changing alpha beta we need a n block. Okay, n block, just change to this value to 0, and another value as minus 0.5. Okay, this will be 0.866 plus 0.866, change these to 0. Minus 0.5. Okay. These two minus 0.866. Okay, now required sum block. Now name this A, this will give B phase, and this will be give 3 C phase. Now connect this to here, B to B, B to B. For A phase, it will be V into alpha. Just multiply this. This will multiply of this A, the alpha into beta, alpha plus beta, and this as well, alpha plus beta, alpha into beta. Okay. Now from here, we had generated our from alpha beta to ABC. Okay. Now we need to generate the pulses for each switches. So take another subsystem and just connect there. A phase, B phase, and C phase. Okay. Now here we need to generate our sinusoidal pulse width. For that, select a repeating sequence and change the value as we have a switching frequency of 10 kilohertz. So it will be 1 by 10,000, 2 by 10,000. Okay. The switching output will be -1, 1 and -1. Except for relational operator and logical operator. So not change, we will distansive use, we will use distansive, and just copy this to for 2 more times. Now connect a phase here and repeating sequence, another terminal to the repeating sequence, B to here and repeating sequence. We'll make the repeating sequence as common. Okay. Now here we required S1, S2, S3, S4, S5 and S6. So we'll connect the before not gate, and in a similar fashion we will connect S6 to here. So here we have generated the PWM, and we have to give to this PWM to our the respective switches. So select go to block. Okay. Change to S1. Okay. S2, S3, S4, S5. Change to S2, S3, S4, S5, and these two S6. Now connect each switch to the respective terminal. S4 to the S4, S5 and S6. Now we will give to S1 to the S1, S2 to S2, S3 to S3, S4, S5 and S6. Scope and power GUI. Okay. Change this to discrete and change to 1 and set a time for 1 second, and let's check our result. Oh, so here need to change the in a current controller, need to change the value to 6.518 for the KP, and KI value will be 6.390. Okay, now let us as we can see that we are getting expected result. The one thing we need to here we need to feed the uh, theta value as well in the transfer from the alpha beta to DQ frame of the current IABC to DQ frame. At the time we have to supply the theta value as well. Thanks for watching. Please like, share and subscribe my channel. Thank you.